Okay, we have another question. This is again from Jan 2025, and this is question number 19. This is from Thermodynamics. This is going to go in the Thermodynamics playlist. So we're looking at the question, and this is, by the looks of it, it looks like it's from an ideal gas equation. So we have a filament bulk, it contains argon gas to extend the lifetime of the filament. Okay. While the filament is off, the argon gas inside the bulb is at a temperature of 290 Kelvin. The pressure of the argon gas inside the bulb is 75% of atmospheric pressure. Okay. Then it gives us the volume of bulb, and it also gives us the atmospheric pressure. And it tells us to calculate the number of argon atoms in the bulb. So pretty simple, you should be able to do this. So we know PV is equals to NKT, and what we have to find here is N, which are the number of argon atoms. So I know pressure is 75% of the atmospheric pressure, so I've plugged in the values. And then volume they have given me in meter cubed, so that's good as well. And temperature is 290 Kelvin, so now I'll just plug the values in, and let me just also manipulate the equation. So N is equals to PV over KT. That's going to give me, I've plugged in the values, and that's going to give me 2.413 times 10 to the power of 21 atoms. Okay, next it says, while the bulb is on, okay, so now we went from the bulb that was off to the bulb that is on. Okay, so our bulb is on and the pressure increases to 83% of atmospheric pressure, probably because the temperature rose. And then it says that the manufacturer states that the temperature of the gas inside the bulb is about 60 degrees Celsius while the bulb is on. Okay, so assess whether this statement is accurate. Okay, so again, it's a pretty similar question actually. So we have PV is equals to NKT, the V volume, N number of argon atoms, and K Boltzmann constant, all are going to remain the same. The pressure and the temperature have changed, and they have given me the pressure value, which is just 83% of the atmospheric pressure. So I'm just going to plug that in, and then I'm going to find the temperature value, the new temperature, okay? The temperature when the bulb is on. So T is equals to PV over NK. So I've plugged in the pressure value as well, which is 83% of the atmospheric pressure, which they actually gave to us before, which is right over here, the atmospheric pressure. And then I'm going to plug in the value. What's the value? Okay, that's 1.25 times 10 to the raised power of minus 4 over N, which we found out just a moment ago. And then I will plug this value in as well. Okay. 0.38 times 10 to the raised power of 23 Boltzmann constant, and let's find the temperature. So that's going to give me 320.9 Kelvin. Now, whenever you wanna change from Kelvin to Celsius, you have to remember that Celsius is equals to Kelvin minus 273. So I'm going to plug it in here. 320.9 minus 273. That's going to give me 48 degrees Celsius, which is less than 60 degrees Celsius. So the statement is not accurate. Okay, next part, it says, while the bulb is on, radiation is emitted by the filament. The radiation has a peak power output at a wavelength of lambda max of 1100 nanometers. So one thing I want you to keep in mind is whenever we are we're taking the bulb, okay, we're taking the bulb, and we take the light of the bulb and we plot a curve, a black body curve, which is going to look something like this, okay? And when you're plotting this black body curve, you assume that this bulb is a black body. Okay, so I want you to keep that in mind. Alright, now we can apply lambda max T is equals to, and we know the Wien's constant to be 2.898 times 10 to the raised power of minus 3. Okay, so now I'm going to find the temperature of this black body, which has 1100 nanometers at as the lambda value at which the intensity is maximum. Okay, so I'm going to find the temperature. Okay, so I have divided by the lambda max value, and I've converted it to meters as well by multiplying it by times 10 to the power of minus 9. And that gives me temperature value of 2634.54 Kelvin. Okay, now to calculate the power output, basically they want us to calculate the luminosity. Luminosity is the power output, the total power output, right? The total power output of all the wavelengths of light that are being given out. Okay, so it's a total power output. So you can say luminosity is equals to the Stefan-Boltzmann constant, area, and temperature to the power of 4. Now we can use this formula because we know the temperature, and we could use the formula above as well because we assumed that it was a black body, and on the basis of that we found temperature. Now we can use this formula as well to find the luminosity, which is basically the total power output. Okay, so I'm going to plug in the Stefan-Boltzmann constant, which is going to be 5.67 times 10 to the raise power of minus 8. And then I'm going to plug in the value of the surface area and the temperature to the power of 4. And I'm going to get the value as 42.4 watts. Okay, then it tells us, suggest why the actual power output might be lower. So this is where the concept of black body helps us. A black body is a perfect emitter and absorber of light. Now, we're looking at total power output. So we calculated the total power output before, but now it's saying the actual power output is less. Now, the only way we can explain this is that we can say that the bulb is not a perfect black body. So we can say it's not a perfect black body, so it doesn't perfectly emit light, and therefore there is the power output being lower as the explanation. So this is the first type of answer. And the second answer you can give is that some of the energy could also be absorbed by the glass, right? So we have the glass here, the glass bulb. So some of the energy can be absorbed by glass as well. So these are the two possible answers, and the one that's preferred by the examiner is the first one, and second preference is this. Now obviously you will be credited for both of the answers. So here's the mark scheme, and you can just look at it and just go through it and hopefully understand the question. And here is the examiner report.